Okay, let me explain what's happening here. We have gone through kinematics, we've gone through forces, and we've done a lot of great problems. There's some problems we did not do though. There's some problems that are hard to do. For example, if you noticed, every time we had friction, we had surfaces that were very straight, right? Every time there's friction, it's flat surfaces, right? Or inclines. We never had a problem where a kid goes down a slide that's like, has got curves on it and there's friction. Because it's hard to do. Some of the problems in forces are very challenging to do. And we have to create different tools for some of the problems that are very hard. And so that's what we're going to get into now. We're getting to the concept of energy for these next two chapters. And this concept of energy is designed to be an entirely different tool set to solve problems that would otherwise be very difficult to solve in forces. Okay? Like I said, the best example of this is more complicated frictions. Frictions that involve more complicated motion. We can do this with energy. It's challenging to do it with forces. You can, but it requires much more complicated mathematics to do it. So that's what we're going to be doing here. We're going to develop in a different tool set. Okay. Now, we're going to segue into this slowly. We're not going to ditch forces completely right now. We're going to work with forces a little bit more here. So let's talk about energy first of all. There's different types of energy we're going to be looking at. The concept of energy is an interesting one. The concept of energy characterizes what effectively is it's a type of state that an object has. And I really would suggest that energy should not really be considered a physical quantity. Okay, it's a state that an object has. It's a state of existence, as you could say. And the most common types of this is it's energy due to the fact that an object moves. And it depends on a couple factors. It depends on how massive something is, and it depends on how fast it goes. And that kinetic energy that object possesses can be converted to other types of energy, which is kind of the benefit of studying energy, is we can look at energy that objects possess and how it can be transferred between different things. Now, what can it be transferred to? Well, we have also a type of stored energy, which we also call a potential energy. And most of the time, potential energies involve aspects of position. So, for example, they're showing the roller coaster here. And when the roller coaster's at the top, it has a lot of potential gravitational energy. And the word potential is actually a decent term here because it kind of represents the potential of an object to do some kind of action. So if the roller coaster is at a large height, it has the potential to fall a great distance. That's a good way to put it. So, and the potential energy depends on the mass of the object, and it depends on how far it can fall. So, by the way, that's just gravitational potential energy. We'll be talking about a couple different ones in this class. There's a potential energy that's associated with elasticity, like springs, for example. And we'll talk about that later. And then, I guess it's not in this class necessarily, but if you take 120, there's electrical, and magnetic potential energies and so on. And then there's another type of energy, which is a complicated type of kinetic and potential energy that is all sort of collectively grouped into what's called thermal energy. And thermal energy just it's an energy that's associated with the temperature of an object and how much of the object is there. And so, an object can receive or lose thermal energy by the transfer of heat. So when heat flows from one point to another, that can change the thermal energy. What thermal energy is going to mean in this class is it's sort of a junk drawer of energy, basically. When energy is dissipated through things like friction or sound or light. When we don't want to characterize the energy in those forms, we kind of just talk about it. Well, this like energy being dissipated or thrown away, and we usually refer to it as thermal energy. I mean, you could see this, for example, if you slide something heavy, right, on the ground at a constant speed, you're doing a push, and then there's friction, right? But it moves at a constant speed, but you're pushing at the same time. Well, a lot of times when you do that, the surfaces, they heat up, right? Because that energy is being taken away and put into the thermal energy of the object. So, all right. So now there is a nice relationship between kinetic and gravitational potential energy that I can show you now. That's done through kinematics. So in the example that we have here on the right, we have an object that is falling under the influence of gravity. So it's starting to drop, right? And we're going to consider the position of this object at some arbitrary place that we'll call a sub I. We consider this object, it's going to be at some initial position y sub I, and it's going to have already an initial speed, which we'll call vi sub y, and it's going to be downward. So, and we're going to consider what happens at some later time. At some later time, the object will be further down at a position y sub f with a new speed that's a little higher, and we're going to call that v final in y. So the acceleration here is going to be minus g in this situation. So we're going to utilize what we call equation 3, the velocity squared equation for kinematics, and we have all our variables here. We have a delta y here, which I'm going to express and with the quantities we defined here. Now, what I'm going to do is, again, take a look at this part here and this part here, right? Now, what we're going to do is we're going to distribute the minus 2g to the terms inside here. And then we're going to rearrange the equation so that all the initial stuff is on one side and all the final stuff's on the other side. Now, this is interesting because we took a kinematic equation, we came up with this strange equation here, which seems to have information about velocity and position. Now, we're going to multiply both sides of the equation by 1/2 times the mass. Now, maybe you might say, like, why are you doing that? Why 1/2 times the mass? Well, I'll tell you later. For now, just realize it's something that you just could do, okay? But there's a reason for it, which it will not be apparent until later in the class. But if I multiply both sides by 1/2 m, then I have these terms here which seem to correspond to the concepts of kinetic and gravitational potential energy. And indeed, they do. These are the terms for these quantities here. Initially, the object possesses 1/2 mv squared. That's the kinetic energy of the object. And it also possesses an mgy, which is the potential energy object. And what's interesting about that is that quantity, when you sum those things up, it equals a number. Some number, doesn't matter what the number is, it's just a number. But, and you look later at this object, after it's fallen a distance and sped up, and those same quantities with the new values of speed and position will equal the same number. And this is a very important thing, and this is the first time you're seeing this in this class. This is what's known as a conservation law. This quantity, which is the summation of kinetic and potential energies, is a conserved quantity. And this will eventually lead us into what is known as the conservation of energy, which is a very powerful tool that we are going to use in this class to solve problems. Okay, so now we're going to properly identify these two things. The 1/2 mv squared is what we're going to define as the kinetic energy of the object. 1/2 mv squared, the m is the mass of the object, and v is the velocity of the object. Now, that has units of kilograms, meters squared over seconds squared. That's a new unit. The unit is called the joule. A joule is 1 kilogram meters squared over seconds squared. Okay, just to give you a sense of what a joule is, imagine taking an apple, and drop it, I don't know, a 1/2 meter off the ground. If you drop an apple about a half meter, that's about a joule of energy. It's about a joule of energy. So, gravitational potential energy is going to be defined as mgy, where m is the mass, g is the gravitational acceleration, and y is the distance. Now, actually, y in this case is a position. It's the position of the object. So, now in this case here, what is going on? Okay, and that the units for that are also kilograms, meters squared over seconds squared. So that is also a joule. Okay. Now what's happening here is there is a transformation of energy. Where the object possesses a bunch of potential energy, it loses it, and then what happens is the kinetic energy increases. We call this energy transformation. This is part of the conservation of energy. And this is what's nice about energy is we can kind of bookkeep it. We can keep track of it. And that's the important aspect of this, is that we can keep track of energy. Let's talk about energy. Now, some students like energy, some students don't like energy. Why? Well, as with anything in physics, there's a certain level of concept and a certain level of mathematics. Some students love the math. They love the math. If it's just math, they're like, I want to just dig into this math and just cuddle up with the math and just feel comfortable. And some people are like, I don't like the math. I like the concept. I like to think about it. I like to make the logical connections between things. And if you're that person, well, energy is your thing. If you're the math kind of person, you won't like this too much, because the mathematics behind this is just as simple as it gets. The math here is a joke. It's so easy. It's the concept that's very challenging. So let's talk a bit about it. Just like in forces, when you look at something, you want to be able to identify systems and environment. Just like for forces, systems and environment, right? And for every object in your system, you can characterize its energy. And the energy can be lost or gained, but it's given to things either that are in the system, where it can also gain and lose things, or it can be expelled from the environment or introduced from the environment. So this figure is an excellent figure here. Let me explain what's going on in this figure here. We have our system. And the objects in the system can exchange kinetic and potential energies with each other. However, they can also transfer some things to thermal energy. When things are transferred to thermal energy, like in friction, for example, that energy is effectively lost. It stays in the system, but it cannot be harnessed in the same way that kinetic and potential energies are. You can actually also have the environment interact. The energy can be put into the system or it can be removed from the system. Okay? So there's a lot, and so we're going to be working with this energy model quite a bit. For the next several lectures, we're going to be working on the energy model over and over and over again. Well, let me give you an example of this. Let's talk about the ball that falls through the air, right? Now, in order to make this make more sense, we're going to talk about drag as well. If a ball falls through the air, it's going to lose potential energy and it will gain kinetic energy. But if I decide to involve drag, then what happens is as the ball falls, there's friction that will occur, drag, right, with the air. That's energy being taken out of the system by the air. The air is the environment. But what happens? Where does that energy go? It goes into likely just increasing the thermal energy of the air. So the energy goes out. But some of the energy, while it leaves the transfer between kinetic and potential, I'm out of water. This is the worst. All right. The ball itself may heat up a little bit. And that's energy being removed from kinetic and potential being placed in the thermal. By the way, just to be clear about this, remember how we did forces? Every single problem was free body diagram, right? What is system? What's environment? Free body diagram. Same thing's going to happen here. What is system? What is environment? We don't do a free body diagram. We do something called an energy transformation, where we consider how the energy moves in the system. Okay, how about this? We have a box on the top of an incline. And the box is able to overcome static friction, and it slides down with a mild acceleration to it. Okay? So it's a box going down an incline with a mild acceleration to it. The box initially possesses a bunch of potential energy. As it slides down the incline, that slowly gets converted into two types. It gets converted into a kinetic energy as it speeds up, and then some of the energy is dissipated by friction, so that becomes E-thermal.
Oh, and that's why you get like some kind of heat between the surface and the thing. Okay.
Right. Now, some of that lost potential energy, I would say that lost potential energy went into three things. It went into the kinetic energy as it speeds up. It went into heating the box up because of the thermal energy, and it went into heating up the incline, which would be the example of energy out.
I see. And then the kinetic energy would describe the energy of the movement, right? Of the box as it's moving downwards.
Right.
Okay.
And energy in would be if I were to put my finger on the other side and kind of push it down the incline as it went. That would be energy in.
Yeah. Oh, okay. I see. Because you're kind of adding to the amount of energy that's going. Okay.
So what we're going to do for today's lecture is we're going to be working on the energy in, energy out aspects of things and thinking about environment. And then we'll think about the system later. But putting energy in or out of the system is what's known as work. Work. Now that term work has a very specific physical definition. The term work in general language has a million definitions, right? But in physics, work means a force applied to an object that pushes it through a distance to increase or decrease the energy of the system. That's what it means. It's a force applied to an object that pushes the object or pulls it or whatever, that either increases or decreases the energy of the system.
I see. And that's why you're saying when it's like transferred between like different energies, the energy isn't lost, it's just moved to like a different form. Because like I kind of see what you're saying.
Shelby, you just said the grand theme of energy. Transformations. Energy is gained or lost and placed other places. That's the beauty of energy. It never just disappears. It goes somewhere. It goes somewhere. And that's the whole strategy in our problems, is keeping track of the energy. That's it. All right, now I have a question for you. A child's on a playground. Swing. The motion at its highest point of its arc. What energy transformation takes place as he swings down to the lowest point of the motion? Now, let me explain what I mean by energy transformation. Very specifically. What is on the left side of the energy transformation is something that our object possesses that it loses. What's on the right side of the energy transformation is what is gained by the object because it lost the other thing. So what do you think is the energy transformation for this thing here?
What is UG again?
That's gravitational potential energy. So U is a universal symbol for potential energy, and there's subscripts that correspond to the different types. G is for gravitational, S is for spring, and so on. E is for electricity and all that. Okay. But yeah, B, huh? I like B because it's right. So this child possesses a bunch of gravitational potential energy at the top of his arc. Now, we're not saying that he only possesses gravitational potential energy. What we're saying is that the child possesses the potential energy and will later lose it.
Can I ask a question about that?
Yes, Martin.
So is potential energy pretty much the highest point in a way until it goes back down? Like as in like a complete stop, but still energy in a way?
Well,
would that be potential energy?
You know why? Because, presumably the child is, we're talking about a picture like this, right? Okay, so that's quite, anyway. So this would be like at the top of the arc and at the bottom of the arc here. Okay, so there's
Right.
like, I don't know how to draw this thing here properly. There's that, and there's like this, and so this thing swings. If anybody makes fun of me, you're gonna get a bad grade the next test. So it's swinging down here. So up here, it has a bunch of gravitational potential energy, and down here, it has some kinetic. It might still have potential energy, but the idea in the transformation is this: it possessed gravitational potential energy and it lost it, and then it turned into kinetic energy. Energy transformations just talk about changes. At the bottom here, does this object still have potential energy? Maybe. Doesn't matter though, because we're only talking about the change. So this is all about changes. What changes? What changes? What changes? A skier is gliding down a gentle slope at a constant speed. What is the energy transformation taking place? What do you think? What do you think? What do you think? Now remember, the question you ask yourself is this: what is possessed by the skier that it loses, and what is gained? C's and D's. C's and D's. I don't like D. I don't like D. Somebody tell me why I don't like D.
Could it be because the
Sorry, say
energy
again?
stored? Could it be the energy stored?
Well,
Like how it's losing in a way?
not quite. Why don't I? Constant speed, Robert. Got it. If the skier is moving at constant speed, that means the kinetic energy doesn't change. A is wrong and D is wrong. So if you're going down the slope, we are definitely losing potential energy. Now B is wrong because B suggests that we gain kinetic energy, but again, constant speed. So the correct energy transformation is gravitational potential energy converted to E thermal. The gravitational potential energy is being dissipated by friction, likely, or drag, or both. But again, the E thermal is like the junk drawer of energy. When we can't identify where else it goes, it's just lost, and that's E thermal. That's E thermal. Yeah. Okay. So now we want to get into the concept of work, because what we want to do is we're going to focus right now on kinetic energy, and we're going to work on that a bit, and then we're going to move to the other stuff. Okay, I already mentioned that work has a very specific meaning in physics. Fantastic. So in this example of Mariano Rivera with his nasty cutters, as he's throwing that ball, he applies a force to the ball. All right? That force accelerates the ball, and that's what in physics we call work. By applying a force to the ball, you increase its speed, and therefore the kinetic energy increases. If I had to describe an energy transformation here, it would look like this. It would be real simple. It's just work to kinetic. Because where does the energy come from? It comes from work. It comes from work. Now, it's just like in forces. Well, how exactly are we doing work? Well, it has something to do with the muscles and chemical energy, and that's not our issue right now. We just know that there's work being done. So that's where the energy comes from, okay? You can say it's like lost by, I don't know, chemical energy. You get tired after you throw a ball a few times, right? That's converted to kinetic energy. Right, now, there is a formal definition for work, which I'm not showing you because I care about you and I don't want to expose your mind to any scary calculus. So, in the know though, the definition of work involves a line integral. But we don't do line integrals here. What we're going to do is we're going to simplify that to say what kind of distance can this force push this object? Okay. So the F sub s here is the component of force along the direction of motion. Okay, because if you look at this force up here, right here, that force is pointing, relative to the axis here, it's up and to the right. Now, if you break that into components, there's a component along the direction of motion. And indeed, that is going to make the object speed up. There is a component of force that's perpendicular to the motion. Guess what that does? Nothing. No work done there. So the F sub s is the component of force along the direction of motion. And then what we do is we integrate that force over the distance traveled, and that tells us the amount of work that's being done. Now, the units of force are newtons. The ds is in meters, which also is a joule, because newtons are kilograms meters over second squared. You throw another meter in there, you got yourself a joule. So we are not done with forces. We will look at how forces interact with our objects to determine how much work is being done, and then from the work we determine what the kinetic energy difference is going to be. So this method here, that's fine if the direction of motion changes. That's fine. But work only cares about the component of force along the direction of motion. If the direction changes, Shelby, that's when you have to get the line integral out. Because the line integral can handle forces and directions that constantly change. We are going to simplify that down so we don't worry about line integrals, because they're not exactly complicated, but it does involve a bit of vector calculus, and we're not, supposed to know any vector calculus right now. Fs is the force along the direction of motion. So, for example, if this was the x direction, we would say F sub x dx. That's the idea, F sub x dx. Okay. So this method here is actually going to blend together forces and kinematics all together. Okay, so let me erase some stuff here. Now, because we're simplifying the mathematics to a great extent, our force will be constant. We will not deal with change in forces. We will not deal with change in directions. We have enough to worry about when everything is constant. So with that definition, to figure out what the force is along the direction of motion, we could simply take the component of the force. That will be an F cosine theta. F cosine theta is the Fs. That's the direction. That's the force along the direction of motion. So we got an F cosine theta here. Now, assuming that's constant, that jumps out of the integral, F cosine s. And then the integral of ds is just the distance. That's the simplest integral you can have, right? So it's just the distance. So this turns into F cosine theta and the difference between the positions, which I'm just labeling here as a displacement vector, delta r. So for a constant force, the amount of work that's done, or in other words, the amount of energy that's taken out of the system or put into the system, is proportional to the force, the displacement, and the angle between those two. So there's three parts to this, right? So if your force is along the direction of motion, so in this example here, our force is along the direction of motion, are just along the direction of displacement. So the cosine is just 1, and it's just F times delta r, which is just force times distance. If our force is at an angle with respect to the velocity vector or displacement vector, then we do need to involve a cosine. Both of these are examples of positive work. Positive work increases the energy of the system. If your force is perpendicular to the direction of motion, that will not perform any work. A force that's perpendicular to the direction of motion cannot increase or decrease the speed of an object. 0 work. It's 0 because the cosine of 90 degrees is 0. Right? If your force is opposite the direction of motion, whether it's at an angle or it's anti-parallel, that's negative work. Now, what I think you should do here, though, is I don't think you should be putting in non-acute angles. I know they're showing non-acute angles here. They're showing obtuse angles. I don't recommend that. Even though the cosine will output a negative sign, I think you got to work with reference angles, which means you would do the angle that's right here. So imagine we just continue this, and the angle that's right there, that's your reference angle. and that has the same value as the supplement that's being shown here. But you need to put a negative sign because the force is in the opposite direction. So, and they're showing that here too. Okay. All right. Oh man, I don't know what's up with all these people and their issues with boxes. Got a lot of angry people pushing on boxes. I don't know what that's all about. Robert pushes the box to the left at a constant speed. In doing so, Robert does what kind of work on the box? It's A.
Why not? It's going
Well,
left.
guess what? Which direction is the force? Let's show. Let's draw it, right? What's the direction of the force? Which direction is the force? The force is that way. Which way is this box moving? That way. That's positive work.
What if it was on an incline?
Doesn't matter. Positive
It
work.
would still.
You're
Okay.
pushing in the direction of motion. That's positive work.
Oh, but I guess I should have been more specific. An incline going up.
That's fine. That's the same.
Same?
Different. No different.
Okay.
Yeah, no different. So it's if I go back to this picture here. You didn't see that. That would be this first example right here. Right? Force to the right, positions to the right. Now, I don't know if you were thinking like, oh, well, the direction's negative. Well, there's two negatives then.
The box was moving to the left, and he was pulling to the right. It would be negative.
There you go. That's negative work. Now, check this out, though. Let's talk about this problem, though. Okay. Now, he's doing positive work on the box, but we're not speeding up, huh? We're moving at a constant speed. What's happening? Why? It's not Robert's fault. What's going on here? Why are we not speeding up?
Is it because
Friction?
Friction. There must be friction. There must be friction. Or like the gnarliest like air resistance you could imagine. But yeah. And so which way is friction here? Friction's
Opposite.
so what kind of work is friction doing?
Negative.
Negative. Yes, I just dabbed. That's how proud I am of you all. All right. Let's go. Good. Now, this is generally true. Going back to our energy model, let's fill in more about what the environment does. If you have positive work being done by an individual agent, that will act to increase the energy of the system. If there's negative work being done, that will act to decrease the energy of the system. So, what things do work? Forces do work. You look at a problem, and we're going to approach these problems in the same way we did before. We have a system. We identify the forces on the system, and then we look at how it moves. We figure out what the positive works are, what the negative works are, right? And then we can determine how the system energy changes. Let's recap a little bit about the stuff we talked about yesterday. And we want to talk about our basic energy model, okay? And the way the basic energy model is working for us here is we have a system. We have objects in the system. And we say those objects will have different states of energy: kinetic, potential, thermal, and they can exchange that energy with each other in that system. There is an environment, though, and the environment can add energy into the system or take energy out. If work is done on the system, we say that's positive work, and energy is being added to our system. Now, the system can do work on the environment, and that would remove energy from the system, and we would call that negative work. Okay, so this is our basic energy model idea. And what we're going to be trying to do is we're trying to keep track of all these things in order to solve our problems. Okay. Now I have some questions for you. Start off here. A tow rope pulls a skier up the slope at a constant speed. is positive or negative work being done on the system. And I'm specifically referring to what the rope is doing. What is the rope doing? Positive or negative work? A lot of A's. I like an A because it's right. Now, there is a concept and some math that you can think about. The concept is that this force is pointed upward or up the slope. The skier goes up the slope. And that's, we learned that work is force times distance, and the force and the distance are in the same direction. That's positive work, right? That's the math. The concept is, if this force were to act alone, would this object speed up? And yes, it would. And so it's positive work. Now, this object is not speeding up, though. It's moving at a constant speed. So what other force is at play here? Somebody tell me. What other force is happening here? What other forces we got? Let's see what you say. Friction? Maybe, and that would do negative work. Gravity? Yeah, that would do negative work. Not tension. Tension is what we already talked about. Tension is the rope, right? We already talked about that. The other forces involved could be friction, could be gravity, right? Normal, good one. Normal won't do any work though, right? Normal won't do any work. It's not pointing in a direction of motion. No, kinetic, no, you wouldn't say kinetics. No, we're talking about just forces for the moment here. Just forces for the moment. Strange. And so if it's constant speed, that means overall there's a network of zero happening here, because friction and gravity would be doing negative work in this situation, right? Bum, 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 moving right along. Skier is gliding down a slope at a constant speed. Now we're going down the slope. Is the environment doing negative or positive work on the system? Now, by the way, when I say environment here, I'm specifically referring to what the slope is doing. Right? What's the slope doing? Negative work, you bet. Now, this thing moves at a constant speed, so there must be some kind of positive work happening, and that would be gravity. Gravity is doing positive work here, and as a result of that, the network is zero, and the speed is constant. Sounds good. Sounds good. I'm very happy you guys said the right letter, because it's right, and you're learning something. And that's my job to teach you. You're supposed to learn. You're doing it. I think things are working. The gears are turning. A crane lowers a girder into place at constant speed. Consider the work done by gravity and the work done by the tension of the cable, which is true. Which is true here. By the way, you don't need to know what a girder is. A girder is a beam. No, it's not a beam. I just settled this in my earlier lab. I thought it was a beam. It's not a beam. A girder is a larger horizontal structural support thing. It's like your spine would be the girder and your ribs are like the beams. That's what I thought. That's the analogy I came up with. That's not my subject, so I honestly do not know. What do you think? Beams are smaller, apparently. Beams are smaller. They're additional supports, where the girder is like, I don't know. C's, huh? I don't know about C. Who started the C business here? Michael. Everybody was on B, and everybody's like, wait a minute, what's going on here? Everybody's on B. No, they weren't. It's Michael's fault, everybody. Michael said C. Actually, it's not Michael's fault. Michael was brave and guessed first. And the answer is B. All right. I'm proud of myself. I'm proud of you too. Okay. BBB, it is. You bet it can. Wait, negative newtons. I don't know that. Let me reword your question for you. I don't know what your question is, actually. Contention of negative newtons. Yes. But if it's negative, that just means the tension points in a direction that we consider to be negative. That's it. I mean, that's the only reason why you would say something's negative. Just points in that direction. But it doesn't mean anything for what the force does, you know? So, anyway, what's going on here? Let's draw a picture. Just draw us a picture. This is the girder. Check that out. What do you think about that girder? Excellent. Any girder geeks up in here? Huh? Got any girder nerds that like love girders and can comment on the authenticity of my girder? No? Okay, that's fine. Gravity's down. Tension's up. Which way are we moving though? We're moving down. Gravity is in the direction of motion. Positive work. Tension is opposite the direction of motion. That's negative work. Sorry, I'm just so impressed with my girder artwork. It's hard to move on. Ooh, I like this one. I like this one so much. Now, ignore the fact that it mentions chapter 6. That was from a textbook I used a year ago. Or two. So, but take that out. A car on a level road turns a quarter circle counterclockwise. You learned in chapter 6 that static friction causes the centripetal acceleration. Well, you learned that in chapter 6. The work done by static friction is what? What's the work done by the static friction? Bam! Robert got it right.
Let's go.
Let's do it. Bring it. Now everybody's saying C. Oh, now everybody's saying C. Oh, okay, I see how it works. All right. It is C. Why is it C? Concept and math. Let's talk about it. Would this force cause this object to speed up or slow down? No. This force acts to keep it in the circle. So the answer is 0. Mathematically, we learned that work is F delta R cosine theta. The angle between the displacement and the force is 90 degrees. Cosine 90 degrees, 0. So mathematically, it's 0. Okay, fantastic. This is true of every centripetal force, or rather, every single perpendicular force. Perpendicular forces will not do any work on objects because the force is not in the direction of motion, meaning that force is not responsible for speeding up or slowing down our object. So therefore, no work is done. Just like if I have my stapler here, right? If I move my stapler toward you, and I consider, what is the normal force doing? Well, normal force is up, but my motion is toward the screen here. And so this normal force is not performing any work because it's not responsible for me moving. What is responsible for this? The static friction of my hand on the stapler does positive work to get it to go, but to get it to start moving. That's what I should say. To get it to start moving. Excellent. Excellent. Now, let me remind you how we said this before. Let me remind you of something. In fact, let me draw it out. Okay. So our definition of work that we developed previously was force times a displacement, which I'm going to call delta R, times a cosine theta. Now, the meaning behind this is if you consider grouping together the F and the cosine theta, if you imagine grouping together the F and the cosine theta, it's like you're saying, what is the component of force along the direction of motion? So like, for example, in the picture that you have here, A may represent your force, and B may represent your displacement. And you're trying to consider the component of force that is along the direction of motion. And that would be something like this line here. But that would be given by a cosine alpha, if I talk about alpha in this picture here. All right. Now, mathematical.
Could,
Yes?
could it also be the reverse? Like, could you also
Yes,
say that B is the
absolutely.
force and A is
Yeah.
the displacement?
Yes. Mathematically speaking, yes. Conceptually, that's a little strange, but mathematically, yes, that's completely right. Yep. So either way is fine, yeah. Now, anyway, my point, though, is that this product, F delta R cosine theta, has a mathematical formalism to it. Now, if you've gone deep enough into mathematics, you may have taken a class called vector calculus, which I believe at AVC is Math 250. And in there, you learn about dot product. Okay. In fact, actually, I teach trig here, or at least I used to. I haven't taught trig in a year, but we do dot products in trig too, actually. Do dot products in trig. But anyway, my point is that we can rewrite this in a more formalized way as a dot product. Now, we don't formally have a lot of vector calculus, so I'm not going to show you what's under the hood here, because what's under the hood is a bunch of matrices. And you're not going to see that. Okay, we're just going to slap the roof of this car and say you can fit so many scalars in this thing, or something like that. Because this is a scalar. This product down here is a scalar. Okay, so we call this scalar multiplication of vectors, or scalar product. But when you multiply these two vectors in this form here, which is called a dot product, you result in a scalar that has the form AB cosine alpha. So that means we can rewrite how things look to look like a dot product. That's the point here. And our dot products have the exact same properties as the way we've dealt with work before. So if your vectors are aligned, right, your dot product is just the product of the two vectors. If you have an acute angle between them, okay, it will be some positive value for the scalar. If it's perpendicular, it's 0. If it's an obtuse angle, it's negative. And if it's a straight angle, or 180 degrees, it's just the product of the two with the negative side. That's the same properties as the cosine, by the way. So that's no different. There's no difference. It's the same properties as the cosine. Same thing we did last time, actually. So let's do an example of this. Say we have vector A with magnitude of 3, and vector B with a magnitude of 4, and a 30-degree angle between them. Okay, the dot product would be the product of the two magnitudes, 3 times 4, times the cosine of the angle between them, which is 30 degrees. We get 10.4. If I put this in the context of work problems, imagine that 3 is our force, 3 newtons. Imagine 4 is the displacement, 4 meters. And say this force acts on the object as it moves through 4 meters. So we can calculate the work that's done by that force. 3 newtons times 4 meters times cosine 30 would result in 10.4 joules of energy. Joules of energy. That's it. Now, we don't always have vectors in magnitude direction format, though. If you have your vectors in direction magnitude format, you do the dot product as I laid out. However, a lot of times vectors are given in terms of components. And when the vectors are in components, certainly you could change them into magnitude direction, but that's a lot of extra work that you really don't need to do. There is a alternative form for the dot product if you deal with things in components. And what that is, you take the product of the I components of the vectors, and you add it to the product of the y components of the vectors. And you will result in the same thing. Okay, so here's another example of that. Say we have these two vectors here. Vector A is 3i hat plus 3j hat. Vector B is 4i hat minus j hat. So if I want to compute the dot product of these things, now here's the thing. If I wanted to compute the dot product of these two vectors and I did not want to go about doing it with this component format thing, here's what you have to do. Pythagorean theorem on both to get their magnitudes. And then you're going to have to work out the angle between them, which means you're going to need a couple of inverse tangents or something like that. And that's obnoxious. It's a lot of extra work. You don't need to do that. So here we take the product of the I hats, which is 12, 3 times 4, and the product of the j hats, 3 times -1. We add that all up, we get a 9. So that's the dot product there. So you're going to see a lot more dot products. This is the extent to which you need to know about dot products. Again, you're not looking underneath the hood. Underneath the hood is a lot of matrices, but we don't need to worry about that. We're just worried about what the values are. So there's 2 ways you can go about doing it based on what information you're given. So just letting you know. So with that being said, here is our new formalization of our expression for work. We can say that work is the dot product of force times displacement. So that's a nice thing to have. So it just looks nicer, looks neater. I feel a little better about it, honestly. All right, so there is a problem that will wrap up this part of the lecture, so let's jump into that problem right now. What I want to do in this problem is I want to calculate the individual work done by all of the forces, I should say forces, not sources, on a 1,500 kilogram elevator car. Okay, the cable, as a cable lifting it to 40 meters at a constant speed, friction average. Okay, so the question asks, calculate the individual work done. Now, because we're doing these work kinetic energy problems, we're just mostly focusing on work right now, you still want to be doing your free body diagrams. We still want to do that. In chapter 6, you still want to be thinking about free body diagrams. In the next chapter, we formally get into the conservation of energy. We don't have to worry about that, but we're still dealing with forces right now. So let's talk about that. On the elevator car, I have my tension going up. I have my gravity going down. And because we're going up, our frictional force would be kinetic, and it would point downward. All right, so now all of these forces are along the direction of motion. So you'll notice that I don't really put my cosines in here because I don't need them. Okay, these are trivial angles, right? And the only thing I need to really be concerned about here is there being positive work? Is positive work being done or negative work being done? So tension's positive work. It's along the direction of motion. Gravity and kinetic friction, negative work. So I'm going to manually put in those negative signs when I do my work calculations here. I could put in cosine 180. I don't like to do that. And in my experience, when students try to do stuff like that, they tend to mess things up. So I'd recommend you don't do that. So anyway, for each of the 3 forces, the work would be the force times the displacement. Of course, there is a cosine, but I already talked about that, right? So now for this first one here, I need to know what the value of the tension is. I don't even know what it is. Okay. Now I'm assuming, now I'm not assuming anything. We're moving at a constant speed. Excellent. So my Newton's second law formula would look like tension minus friction minus gravity. So that means tension is equal to the sum of gravity and friction, which I got to be 14,800. So I multiply that by the 40 meters of displacement, and I get a nice 592,000 joules. Okay. The work done by friction is so tiny, it's only 100 newtons, the forces. So we get negative 4,000 joules. The work done by gravity is very large. I put in with the gravitational forces, mass times g, times the displacement, and I get that. So those are my answers for the different works being done. And it says additionally, what is the net work? What is the total work or net work? You just add them all up, and we get a 0, which is good because we were told that things are at a constant speed. And so if we didn't get a 0, it means we made a mistake somewhere. Okay. So, but if we didn't get a 0, by the way, say we didn't know this was constant speed. Okay. Say we didn't know this was constant speed and I somehow knew the tension without having to do this garbage over here. If I do my network and I get a positive value, well, then we are speeding up. And if I get a negative value, we're slowing down. That's it. That's how those are done. Any questions about this problem here?
I'm just still a little confused on how you got kinetic friction to go down.
Oh, well, it says that we're lifting the car. We're lifting the elevator car. So that means the velocity vector here is upward. And remember, kinetic friction is always opposite the direction of motion, so it's got to be down.